This text was written by a model that did not exist 2 hours ago. No downloaded weights, no ready-made tokenizer library. We took a Wikipedia dump, cleaned it ourselves, learned our own vocabulary, wrote a transformer in plain PyTorch, and trained it on our own GPU. In numbers, that is 59.6 million parameters and 50.55 million tokens of training text. Let us be honest up front. This is not a chatbot and not an assistant. A model this size learns spelling, grammar, and the register of an encyclopedia, but it states falsehoods confidently and loses the thread after a sentence or two. We will look at its real output with no cherry-picking. Now let us walk the whole path, from an empty folder to a working model. The whole path fits into 7 steps, and each one is a separate runnable script. Download a Wikipedia dump. Stream through gigabytes of XML. Turn markup into clean prose. Learn our own vocabulary with byte pair encoding. Encode the entire corpus into a flat array of numbers. Train the model. And measure the result with honest metrics rather than a pretty picture. At no step do we take somebody else's pre-trained artifact. The only thing we borrow is tensors and automatic differentiation. Everything else we write ourselves, and that is exactly why, by the end, you will understand how this thing works on the inside. We start from a literally empty folder. We create a virtual environment so we do not pollute the system and install PyTorch. Here is an important detail for new graphics cards. For the Blackwell architecture, that is the 50 series, you need the build for CUDA 12.8. Install the ordinary build and Torch will see the card but will not compute on it. And right away we run a check that must not be skipped. We ask Torch whether CUDA is available, and multiply 2 matrices directly on the card. If that script runs, you can stop doubting your environment. Mine is an RTX 5080 with 16 gigabytes, and the model will use under 5. 8 gigabytes is enough too. We take the data from the source. Wikimedia publishes full dumps of every edition. The file simple-wiki latest pages articles.xml.bz2 is 354.5 megabytes compressed. Here is the first real trap, and almost everyone hits it. The server answers with code 403 if you do not identify yourself. Wikipedia requires the client to send a meaningful user agent header. Add it and the download runs. We also support resuming by byte range, so a dropped connection at the 300th megabyte does not cost us the whole file. Note that we use no external networking library at all, only the standard ERLB module. Inside the archive is one enormous XML file. You cannot read it into memory. The Russian dump alone is almost 2 gigabytes of article text once unpacked. So we stream. The iterparse function yields events as it reads, and after each finished page we call clear and release the memory. As a result, memory use does not depend on the size of the dump at all. We keep only genuine articles. Namespace 0, no redirects and no service pages. On the English edition that gave 283,997 articles in 50 seconds, on the Russian 175,897. Now the most underrated part of the whole project. Cleaning. Wikipedia markup is neither HTML nor Markdown. It has nested templates in double braces, image captions, footnotes, and tables. Feed that to a model as is, and it will faithfully learn braces and pipes instead of sentences. A regular expression cannot remove nested templates, because a template can sit inside a template. So we write a small scanner that walks the string once and tracks nesting depth. Links in double square brackets become their visible text, while images and categories are dropped entirely. From that markup we got 194.3 million characters of clean prose. Let us look at the result with our eyes, not just at the file size. On the left is the start of the Russian corpus, ordinary encyclopedia paragraphs. We check for leftover markup. Across 517.3 million characters, only a handful of double brackets survive. That is a fraction of a percent. But there is an honest loss, and it deserves to be said out loud. Along with the templates, we threw away the numbers that lived inside them. So in places you get area, dash, square kilometers with the figure missing. Keeping them would mean writing an interpreter for Wikipedia templates, which is a large project of its own. We pay that price deliberately and say so. A model cannot read letters, it works with numbers. So the text must be cut into pieces and each piece given a number. The two obvious ways are both bad, and it pays to see why. The first is to cut into bytes. The vocabulary is tiny, only 256 values, but sequences become several times longer. For Cyrillic it hurts especially. One letter takes 2 bytes, and half a letter is not a character at all. The second way is to cut into words. Then the vocabulary is endless. In Russian, a single word has dozens of forms, and any unknown word simply cannot be written down. We need the middle ground, and it is called byte pair encoding. The idea is almost embarrassingly simple. Start from bytes. Count which pair of neighboring symbols occurs most often, and glue it into one new symbol. Repeat as many times as you need. Frequent combinations assemble themselves into syllables, then prefixes and endings, then whole words. A naive implementation recounts all statistics after every merge, and on a 100 megabyte corpus it runs forever. So we do what grown-up libraries do. We count frequencies of unique words, keep an index of which pair appears in which words, and take the maximum from a heap with lazy deletion. Then one merge only touches the words that actually contain that pair. On the Russian corpus I hit a real problem, not a textbook one. Training the vocabulary ate 12.5 gigabytes of RAM and killed a neighboring process. The cause is clear once you look at the statistics. The sample had almost 900,000 unique words, and most of them occur once. Typos, rare forms, transliterations. They barely affect the merge statistics, yet they consume all the memory because we keep an index entry per word. The fix is to learn merges only from words seen at least 3 times. That left 306,000 unique words, covering 97% of all occurrences. Memory is fine, and the vocabulary is practically unchanged. Let us look at what it learned on its own. We did not hand it a single word. Among the longest learned tokens are whole words, and in Russian even a 20-letter one. The model receives such a word as one number, not letter by letter. Compression is 7.37 bytes per token in Russian and 4.25 in English. The difference is honest. Cyrillic takes 2 bytes per letter. An important property is reversibility. Any text encodes and decodes losslessly, including words that never appeared in training, and even emoji. An unknown word simply falls apart into smaller pieces. There is a test for that. During training, we must not waste time on tokenization, so we do it once. The whole corpus becomes a flat array of 16-bit numbers on disk. 16 bits is enough because our vocabulary is 16,000, well under 65,000. Training then simply memory maps that file and slices random windows out of it. Article boundaries are preserved with a special end-of-text token, so the model can see where one document ends and another begins. The last 0.5% is set aside for validation. That is essential. We will measure quality on text the model has never seen. Russian gave 142.32 million tokens, English 50.55. Before writing the network, we need to understand the task. It fits in one line. Predict the next token. That is all. No labels and no teacher's answers. Take a window of text, and the correct answer for every position is the same text shifted right by 1. That is the entire labeling, and it comes from the text itself for free. Notice an important detail. We do not predict a single next token at the end of the window. We predict every position in parallel. With a window of 256, that is 256 training tasks from a single pass. That is precisely why training is feasible at all. And the causal mask guarantees that when predicting position number 5, the model sees only the first 4 and cannot peek at the answer. A token is just a number in the vocabulary, and by itself it means nothing. Number 1200 is not bigger or better than number 100. So the first thing we do is map every number to a vector, a row in the embedding table. These vectors are not specified. They are learned along with everything else. That is where meaning settles. Words used similarly get similar vectors. The second term is the positional embedding. Attention on its own does not know word order. To it the text is a set. So we explicitly add a position vector. At the output, the network produces one number per vocabulary token called logits. Cross-entropy turns them into probabilities and penalizes the model for giving the correct token a low probability. The loss is in natural logarithms, and raising it to the exponent gives perplexity, an understandable measure of uncertainty. Now the model itself. It is a decoder transformer, and it fits in a single file. The heart is causal attention. Each token looks at the previous ones and decides what matters right now from everything read so far. One matrix produces query, key, and value at once, which is cheaper than 3 separate ones. Then the channels are split across heads, so different heads can watch different relationships. The is_causal flag applies a triangular mask. Looking ahead is forbidden. If a token could see the future, the model would simply copy the answer and training would be pointless. This is not a declaration but a checkable property. We have a test that changes the last token and confirms that the outputs at every earlier position do not move by a single bit. Let us go through the operation step by step, without formulas on a blackboard. Every token has 3 roles. The query, what I am looking for. The key, what I represent. The value, what I hand over to whoever is interested in me. The dot product of one token's query with the keys of all previous tokens gives similarity scores. Those are then divided by the square root of the head dimension. That is not decoration. Without it, at large dimensions the values spread out, the softmax saturates, and the gradients nearly vanish. Then softmax turns the scores into weights that sum to 1, and we take the weighted sum of the values. We have 10 heads, and each works in its own subspace. One may track agreement, another the topic. We call the ready-scaled dot product attention kernel, and that is not cheating. The mathematics is exactly as described. It is simply computed efficiently in one fused kernel. Now, honestly about the hyperparameters, because they are usually just handed to you as a list. A vocabulary of 16,000 is a compromise. A larger vocabulary means shorter sequences, but a fatter embedding table and more rare tokens that train poorly. The window of 256 tokens is chosen for the data and the memory. Attention cost grows quadratically with window length, and it is the most expensive decision here. Depth 10 and width 640 give 59.6 million parameters. The width must divide by the number of heads. Otherwise, the channels cannot be split across heads. A learning rate of 6 × 10 to the -4 is a standard working point at this scale. And the most important rule, which I suggest you remember. Model size should be chosen to match the amount of data, not the size of your GPU. We have little data relative to the card's power, and we will see that on the curve very clearly. The block follows the pre-norm scheme. First normalize, then attend, and the result is added back to the input. Then the same with the feed-forward part, which widens the representation fourfold and projects it back. These residual connections let us build a deep network without the gradient vanishing. Then 2 tricks that buy a lot for almost nothing. First, weight tying. The embedding matrix and the output layer are literally the same matrix. That saves 640 times 16,000 parameters and reliably improves the loss. Second, scaling the residual projections by the square root of twice the depth. Otherwise, the variance of the residual stream grows with the number of layers. The result is 10 layers, 10 heads, 59.6 million parameters. Before we occupy the GPU for an hour, we run 2 checks that catch almost every mistake. The first is the initial loss. An untrained model must be uniformly unsure, which means its loss should equal the natural logarithm of the vocabulary size. For our 16,000, that is 9.68. We measure and get 9.83. That matches, so the initialization is correct. Had it come out much lower, information leaked somewhere. The second is overfitting a single batch. Take one small chunk of data and train on it for 200 steps. A correctly wired network must memorize it, and the loss drops to nearly 0. If it does not, the backward pass is broken, and no amount of training hours will fix that. The loop itself is a couple of dozen lines, but every detail in it costs money and time. Take a batch, predict the next token at every position at once, measure the error, compute gradients, and nudge the weights. That is all of training. We compute in BF16, twice as fast, and unlike FP16 it needs no loss scaling, because it keeps the exponent range of ordinary float. Gradient accumulation lets the effective batch be larger than memory allows. Warm-up stops the first steps from wrecking the randomly initialized weights, and cosine decay squeezes out the last of the quality at the end. Weight decay is applied only to matrices. Decaying norms and biases hurts. And we clip the gradient so that one bad batch cannot blow up the run. We launch it and watch the curve. The start is 9.83, which is pure ignorance. For the first 1,000 steps, the loss falls almost vertically. At this moment, the model learns the cheapest regularities. Which characters exist at all, that a period is followed by a space, that words are separated, which letters occur together. By step 2000 the uncertainty drops from 18,500 options to 33. Then the hard part begins, grammar and agreement, and the curve visibly flattens. Every 250 steps we measure the loss on the held-out split and, if it improved, we save a checkpoint. We save on validation, not on training loss, and in a moment it will be clear why that is essential. And here is the main plot twist of training on limited data. Our English corpus is 50.55 million tokens, while the GPU can chew through many times more, so the model passes over the same text again and again. At some point, the curves diverge. The training loss keeps falling, while the held-out loss turns upward. That is overfitting. The model memorizes particular sentences instead of learning the language. The best checkpoint landed at step 11750 with a loss of 3.0358, and by the end it had degraded to 3.0709. We keep the best one, not the last. This is why you must not pick a model by training loss. It improves even when the model is already getting worse. Pretty example proves nothing, so we measure. The main metric is perplexity. It answers the question, between how many equally likely options was the model torn at each token. But the number alone means nothing, it has to be compared against something. So we take 2 honest baselines. The first is uniform guessing over the whole vocabulary, that is 16,000 options. The second, and far more important one, is a model that knows only token frequencies and nothing about context. Our model must beat that one convincingly, otherwise it learned letter statistics rather than language. The result is a perplexity of 21.06 against 1,584.84 for the frequency model. Let me go through the traps people hit, and one of them I hit myself while making this. Training the vocabulary on the Russian corpus 812.5 gigabytes of memory and killed a neighboring process. The cure is the word frequency guard we covered earlier. The second common problem is running out of video memory. The cure is not a smaller model but a smaller batch together with more gradient accumulation. The effective batch stays the same while peak memory drops. Third, the loss does not fall at all. Almost always that is either too large a learning rate or a forgotten gradient reset. 1 minute with the overfit a single batch test tells you which. Fourth, nans appear. Look at gradient clipping and at your compute format. This is exactly why we chose BF16 over FP16. It keeps the exponent range of ordinary float and is far more stable. Now generation, and here there are two dials worth understanding. Temperature flattens or sharpens the distribution. Below 1 the model is safer and duller, above it bolder and more incoherent. On the left temperature 0.2, on the right 1.6, and the difference is plain to see. The second dial is top K. We allow sampling only from the K most likely continuations, which cuts off the very unlikely tail that usually makes text fall apart. Notice what happens at high temperature. Grammar starts to crumble and non-existent words appear. That is not a bug. It is exactly what we asked for. Let us look at the generation loop itself. It is simpler than it seems. We feed a prompt, get a probability distribution for the next token, take only the last position, divide the logits by the temperature, cut off the tail with top K, turn it into probabilities and draw a lot. The chosen token is appended to the sequence and the whole thing repeats. One detail is essential. Our context window is 256 tokens, and once the text grows longer we feed the model only the last 256. So the model physically does not remember the beginning of a long text. That is not forgetfulness, it is the window size. And that is why the topic drifts. One more thing, we draw a lot rather than take the maximum. If you always take the most likely token, the text collapses into repeating the same phrase. Randomness here is not a bug but a necessity. Let us look at the real output with no cherry picking. The model holds grammar, cases, and the encyclopedic register. It starts a sentence correctly and ends it sensibly. And it will also calmly state falsehoods and lose the topic within 2 sentences. That is exactly as expected, and here is why. It has 59.6 million parameters, 50.55 million tokens of text, and 72.4 minutes of training on one GPU. Large models have thousands of times more of both. Besides, we only did pre-training. There was no instruction tuning, no alignment, no fact-checking. So this is a language model in its purest form. It models language, not truth. You must not use it as a source of facts. A point that is almost always skipped, and it matters. Wikipedia text is not public domain. It is published under the CC BY SA license, which means attribution and sharing derivatives on the same terms. The practical conclusion is simple. Do not publish the extracted corpus as your own dataset, credit the source, and respect Wikimedia's rules when downloading. That is exactly why we identify ourselves honestly with a user agent and do not hammer the server with parallel streams. And separately, the thing people do not like to say. The legal status of the weights themselves, trained on such data, is not settled across jurisdictions. I am not a lawyer and will not give advice. For a learning project on your own machine there is no question, but if you plan to commercialize it, that is a conversation with a specialist, not with a video. It helps to understand the scale we are working at so as not to build illusions. Our card delivers about 110,000 tokens per second during training. In 72.4 minutes, the model saw roughly 393.2 million tokens. That sounds impressive until you compare. The corpus holds only 50.55 million tokens, which means we passed over it several times, and that is our real problem, not the hardware. The card could digest an order of magnitude more text if we had it. Hence, the practical conclusion. If you want better results, take more data first, not a fatter model. The full Russian dump is 6 gigabytes instead of our 400 megabytes, roughly 15 times more text, and it is the cheapest improvement available. Growing the model without growing the data gives exactly the diverging curves we saw. The whole path runs with one command. The run_all script goes through all 7 steps in order and stops at the first failure rather than pretending everything is fine. There is a quick mode. It takes a small sample and trains for a few hundred steps. The point is to confirm the whole chain works before you occupy the GPU for an hour. I recommend always starting with that. And separately about the tests. There are 10 and they check not imports but the claims I made in this video. That the tokenizer is reversible. That cleaning removes markup. That the initial loss equals the logarithm of the vocabulary. That the network can overfit one batch. And that attention cannot see the future. If you change the code and break something, the tests will catch it. Let us sum up. We went from an empty folder to a model that writes coherent text. And at every step we understood what we were doing and why. If you want to continue, there are 3 directions and they pay off in this order. First and strongest, more data. We took one chunk of the dump and the whole dump exists. Second, more context and more parameters, but only together with more data, otherwise you get exactly the diverging curve we saw. Third, instruction tuning if you want an assistant rather than a text generator. All the code is in the archive, runs with one command, and is covered by tests. Train your own model and show what you got.